So in today's class, we are going to discuss Hough transform, and it is basically used to detect lines and circles in any given image. So let us first discuss some introduction. Uh, so in previous classes, we have seen some basic features like edges and corners, but sometimes we need some high-level features present in the image. For example, we need to detect the presence of lines or circles in the image for various tasks. Whenever we need high-level features, this basically requires the association of a model with the features that are present in the image. Right? For example, your features could be some set of pixels, and then you want to associate those set of pixels to find out what model actually fits there, whether they all fall on a line or they all fall on a circle and so on. So when we are doing when we are detecting the high level features, we have to basically look for a suitable model, and then we have to also look for some features. For example, our model could be a line, or it could be a circle that we want to see in the image, that we want to basically find out if that is present in the image or not. And features could be, for example, edge points, or there may be some other features, for example, corners, etc. So with the help of model, we will decide a model, and then with the help of the features that we are going to take from the image, we can actually compute some high-level features. And in this particular class, we are going to see how to detect line given some set of features. Okay. So in general, as I'm mentioning here that we are going to detect line or circles, but in general, actually we can detect any shape. For example, you see here we are with the help of pixels which are falling on the boundary of the car, we are trying to detect the boundary, or we are going to actually define the association between the boundary points to get this kind of model. Okay. So now the very obvious question comes: why do we need to fit the models? Why can't we just, as in the previous slide, I said that you can consider the edge points as features, and then you can fit a model on that on those edge points. So why do we need to fit a model? Why can't we just consider the edge points and we can work with them? Okay. So when we are considering the edge points, let's say for example, those points are the discrete points. We don't have any connection between the given two or more points. Okay, but sometimes if we know the connection, if we know that those edge points fall on the circle or they fall on the line, then actually this information can be used to accomplish various computer vision tasks. Okay, for example, let's say your objective is to differentiate between the forest and man-made buildings. Okay, so we know that if you do the edge detection of the forest image and edge detection of the man-made structure like this kind of building, then in the building you will find linear structures. In the forest, you will not find any linear structure. So given the two images, one from the forest and one from the building, if you just do the edge detection and try to find out the existence of lines there, you will find that the line will only exist in case of buildings. They will not exist in case of the forest image. Okay. So by using this feature, very easily we can differentiate forest image from the building. Okay. Similarly, let's say you have to detect the road presence of road, or you want to, let's say, mark the road in the given image. So in that case also, you can, from the edge pixels, you can associate those edge pixels and define the edges or the boundary of the road, and then by marking the boundary of the road, you can precisely define what area in the image actually constitutes the road. Okay. So there are a few examples where if you have these kind of high-level features, we can perform various types of tasks. Okay, so that is why we are interested in computing these high-level features. Okay. Now, what are the steps to get these high-level features? So whenever we are going to detect any high level features, first we have to say choose a parametric model, or we have to choose a model in simple words we can say, which will actually associate the feature points and present a representation for them, right? We can consider the example of, let's say, the line. Let us say you want to differentiate the forest picture from the man-made structure. So in that there we have, let's say, considered that our model will be a line. Okay. So first we have to choose a model, and then whatever the features we are considering, for example, as we said that edge pixels can be considered as features. So by analyzing those set of features, we have to find out to which model they fit in. Okay, and that way we define the model completely. Okay, whenever we are defining the model for given set of features, the membership criteria, it is not a local thing. Membership means given a feature, you want to find out whether this particular feature point falls in a particular model or not. So that cannot be decided by just looking at one point. We have to, let's say, for example, you want to fit a line, so then you need a group of pixels or a group of features to tell if there is any line existing in the image or not. Okay, so there are three main questions when we are going to do for the model fitting. First is, as I just said in the previous slide, what model you are going to choose, right? What model you feel that represents the set of features that we are considering in a particular problem. Similarly, once the model is decided, we have to find out that how many such model exist. Okay. As you see in this example, our model is the line, and we see that there are two lines existing in this image or for these features. Okay. So first thing is to decide which model you feel that is appropriate for the given set of features, and the second is once the model is decided, then we have to find out how many such model instances are there in the image. And once that is decided, for every feature point, since there are several models existing, so for a particular feature point, you have to find out to which particular model that particular feature point belongs to. Okay. So these are the three basic questions that we need to actually analyze when we are doing the model fitting. There are a few challenges. So in the rest of the lecture, we are going to discuss this whole thing with respect to lines. So our model is going to be a line here. So when we are, let's say, doing the line fitting, and we can also consider that our features are going to be some set of pixels, and normally these pixels will come from the edge detection. So the pixels that we are going to consider here, mostly they are the edge pixels. So given the edge pixels, we can simplify this problem. We can say that given the edge pixels, we are trying to fit line in those edge pixels. Okay? Or we are trying to find out if the set of pixels in the given image where a line can be fitted. Okay, so there are some challenges when we are doing this line fitting. When we have the multiple models, as we saw in the previous slide, when we have multiple models, it is we have to find out a particular feature point. Let's say this one falls on which particular model, whether it falls actually on a particular model or it doesn't fall on any model. So this is the first thing. Second, sometimes we find that there is one line existing in the image, but it is difficult to detect that complete line continuously. For example, there are some set of points lying here like this, and there are some other points here lying like this. Though they all fall on the same line, but there is a break here. Right? You don't have any pixels for this duration. So how to handle these missing points? And sometimes when the noise is present in the image, that also creates a problem. So detection of existence of line when the noise is there in the image, that again poses another challenge. Okay, so now let us see what is the way ahead. So whenever the feature points are given, we can have a very straightforward way of finding out whether these feature points fall on a line or not by choosing some set of points from these feature points and then trying to find out if there is any line existing for them, right? For example, you have, let's say, n points here. So you can choose out of n points some k points and then try to find out if those k points fall on a line or not. And then this k can vary from, let's say, minimum 2 pixels to the maximum all the pixels that are there. So this may be a very crude way. You may think that consider some set of points and then see if they fall on a line or not. Okay, but this is not feasible actually to check these all combinations. It's not possible to consider some k points from all these given points and then see if they are falling on a line or not. Right? So we need a systematic way to do this. So that's where actually this Hough transform comes into picture. Hough transform provides us a systematic way of detecting these models like lines or circles or even generic shapes by using a method which is based on voting. Okay? So we'll see the details of this here. So from this previous discussion, one thing is clear that what is our input? Our input is in terms of some set of points. Okay, and what is our expected output? Let us say, for the simplicity, if we have just these 3 points, then we want to find out what is the line which fits in these 3 points, right? Or what is the line which actually passes through these 3 points? So given the feature points here, our objective is actually to find out the model parameters. Now here our model is the line, so we can say that our objective is to find out actually the parameters that can define a line which passes from these 3 points. Right? So let us say if you are considering that your line equation is y equal to mx plus c, then given these points x1, x2, x1, y1, x2, y2, x3, y2, y3, let's say, we want to find out what is the value of m and c for which the corresponding line will pass from these 3 points. Okay? So overall, our objective is to consider these feature points and find out the model parameters corresponding to which the model fits into these given points. Okay? So in case of voting, what we do is a kind of general technique where we let the features vote for all models that are compatible with it. Okay. So in the case of in case of voting technique, we cannot directly go from these features to the model. What we do here, we consider these feature points one by one and then see for a given feature point, what are the possible model parameters, right? So you can say that we can just consider 1 point and see what are the possible values of m and c for which a line will pass from this point, or what are the possible values for m and c for which the value will pass from this point or from this point. And for this analysis, whenever we are considering a particular point, that point will actually tell what are the possible values of m and c for which the line can pass from that point. So that way we can say that every given feature point in this, in the input, will actually vote for a particular model parameter. So we can see that wherever there is existence of line, or if there is a line where these all points are lying, corresponding to that line, whatever model parameter you have, that will get maximum votes, because all these three will be telling that yes, this particular line can pass from this point, or from this point, or from the third point, right? So for every point, we will see that common parameter will get highlighted. So in the, we can say in some sense that particular model parameter m and c will get the maximum votes, and based on that we can decide that particular the line that corresponds to that particular m and c will actually pass from all these 3 points. So step by step we are going to see the details of this whole process, but I'm just briefly telling you here this so that you can understand what exactly we mean by voting when we are saying that we are voting for the model parameters. Okay. So in this process of voting, as I just explained, what we have to do, we have to cycle through all the features, whatever the features we have in the input image, like we have here the 3 features. We have to cycle through all those 3 features or all the available features, and then we have to see that every feature cost votes for the model parameters, and we have to then once this step is done, then we have to look for a model parameter where the maximum votes have been obtained, or where the lot of votes have been obtained, and based on that, we can actually decide an appropriate model. And when we are actually following this voting based method for deciding the model, or when we are using this voting based method to fit the model, this can actually handle noise and clutter also up to much extent. Okay, we'll see how. And also, this can even handle the existence of multiple fragments. As I just stated in the previous slide, that if, let's say, there is a break, there was a common line, but there was a break. So how to find out whether these two lines actually belong to the same larger line or not. So that can be also actually handled here when we are using this voting based method. All right. So now let us see the Hough transform in more detail. So the main idea in Hough transform is to for given feature points, or for simplicity we can assume the given edge points, we have to actually record all possible models or all possible model parameters, and then we have to look for a model or model parameters where we get the maximum votes, and then based on that we can decide the existence of the model. Okay. Now there are two things that we are going to use here. The two nomenclature that we are going to use in this whole discussion. Let us define that here. One is the image space and another is the Hough space. So in image space we have XY points. Okay. For example, if this is the image space, in this image space, the line is represented by a set of XY points, right? So we have a line here in the red color. To define this line, we have to find out what are the points which are actually constituting this line, right? So in the image space, line is nothing but set of XY points. Now, to represent this line, there's one way that you can tell that we have a line in the image where the coordinates of the pixels are x1 comma y1, x2 comma y2, x3 comma y3, and so on. This alternate way to tell this line is by stating the values of parameters, the model parameters, the line parameters which define this line. Okay. So if you know that, let's say, a line y equal to mx plus c passes from these points, then if you just tell the value of m and c, that will be actually enough to state, that will be enough to define this line. Okay, you don't need to tell all the points that are there on the line. Okay, so when we are moving from image space to the Hough space, or this is also called the parameter space, in case of line, or in general, you can say that in the image space, any model is represented by using set of points. But in the Hough space or in the parameter space, the model is represented by using the model parameters. Right? So we can consider this example of line here. So if there is a line, let's say, which is defined in the image space by set of these 5 points, this same line can be defined in the parameter space if we just state what is the value of b and what is the value of m for this line. So we can say that the line, line which was a set of points in the image space, that becomes just one point in the model space or in the parameter space or in the Hough space, we can say. Okay. So, or in other way, we can say that in image space you see a line, but that line becomes a point in the Hough space. Okay. Okay. Now let us see the steps how we are performing, I mean, like how we are going to fit the model in the Hough transform. So let us say, and please remember that in the Hough transform, every feature point is going to vote for a model parameter. Okay? In the image space, you will have feature points. And in the Hough space, you will have the model parameters. And we have to consider the feature points one by one, and every feature point is going to vote for a model parameter, and then whatever model parameter which gets more votes, that will decide the appropriate model. Right? Please remember this in this whole discussion. So now let us say there is a point here in the image space, this particular point. Now we have to find out what can be the model parameters for which we can have a line which will pass from this point. Okay, so as you know, there are multiple lines which will pass from this point. Let's say this is one line which is passing from this point. Similarly, it could be this line also which passes from this point. There could be this line which passes from this point. There are so many lines which can actually pass from from this point. So now, I mean, we may think that how to find out all those possible m and I mean all possible model parameters. This can be very easily done by considering the model. Let's say we have a model that we are considering here for line like this, y equal to mx plus c. So if you are saying that this particular line passes from this point x naught y naught, then this x naught y naught will satisfy this line. So we can say that this will be y naught equal to mx naught plus c. Okay. Now our objective is to find out what are the possible m and c for which the lines that are going to be defined from this, they will all pass from this point. Right? So from this we see that if you choose a particular c, whatever corresponding m that satisfies this line we get, that particular combination of m and c will define actually a line which will pass from this particular point. So how to find out all those possible m and c? That can be easily possible. That can be very easily computed. We can consider that we can do little manipulation on this line, and we say that this line can be actually written like this: b equal to minus x naught m plus y naught. So this is basically again a question of line. So to find out what are the possible b and m which satisfies this line, we have to simply plot this line with respect to b and n, and all the b and m which are falling on this line, they will be actually the suitable b and m for which the line will pass from this particular point. Okay. So if this point is represented by x naught y naught in the image space, we can say that all the possible values of m and b for which if we define a line and that line will pass from this particular point, those m and b are nothing but all the points in this parameter space which are falling on this line b equal to minus x naught m plus y naught. Okay, so what we have to do to find out all those possible b and m for this particular point, we have to just plot that corresponding line in the parameter space. Okay, so for given x naught and y naught, we have to just plot the line b equal to minus x naught m plus y naught in the parameter space. So whatever the points that you are getting through this line, like for example all the points here, corresponding to that, whatever b and m you have, that will define a line which is actually passing from this x naught and y naught. Okay, so with respect to our previous discussion, we can say that this particular point x naught y naught, it has voted for various model parameters b and m in the parameter space. Now what are the parameters, what are the model parameters in the parameter space for which this particular point has voted? So those are the parameters which are actually falling on this line. Okay, so we can say that this x naught and y naught has voted for this particular bm, this particular bm, this particular bm, this particular bm for these points, right? I mean, I'm just writing the discrete points, but if you have if you can mark more points, you can say that for all those all those points of M and B, this particular point X naught, Y naught has voted. Right? This basically means that for all those parameters M and B that we are getting from here, corresponding to them, if we get a line, that line will pass from this point. Okay, so we have initially, let's say, one point X naught and Y naught. X naught and Y naught is actually telling us the possible values of B and M, for which if we make a line that will pass from, that line will pass from X naught and Y naught, and all those possible B and M are denoted by this line, right? So, or in other way, we can say that this X naught and Y naught actually votes for all those values of M and B, which are actually falling, we can say, in something on this line, right? On this line, if you can extend this line, whatever range you have for M and B, in that entire range, this line will exist, and for all those values of M and B, we will have the corresponding line passing from X naught and Y naught. Similarly, so we can say that X naught and Y naught has voted for all those M and B, that are falling here. Now let us consider the another point X1 and Y1 here. So X corresponding to X1 and Y1, to find out what are the possible M and B, we'll see that there will be another line explaining or giving us the possible M and B. So we can say that this line is here. So all the M and B that are falling on this line, they will actually give us the values of M and B for which the corresponding lines will pass from this particular point. Now, in this whole thing, when we are plotting the corresponding line in the parameter space for these 2 points, we see that there is one point where these 2 lines are intersecting. Right? Let's say this particular point. On this particular point, these both lines are intersecting. So what basically that means? This means that this particular B and M, corresponding to that, if we get a line, that line passes from this point also and this point also. And we are actually interested in finding out such B and M for which we have multiple points actually satisfying that particular line pass. Okay? So in this particular case, wherever this intersection is existing, this basically tells us that corresponding to that B and M, you have 2 points which are actually falling on that line. Okay. Now, if you just see that, if you just keep increasing the number of feature points in the image space, we will say that corresponding to those points, we will find new set of B and M values in the parameter space, or in simple words, we can say that corresponding to every feature point in the image space, we will get a new line telling us the possible values of B and M for that particular point. So for 3 points, we see that all these 3 lines, if we plot, they look like this. So now, given this information, to find out, we can say that if let's say this is the mapping we have. These were the image points that were given to us, or these were the feature points given to us, and corresponding to those feature points, we have plotted the possible values of B and M in the parameter space. So we can say that corresponding to every feature point in the image space, we have these feature points have voted for possible B and M in the parameter space. Now, in this whole space, we see that there are some, if we let's say divide this whole space into grid, then we see that there are some points where all these lines are intersecting, right? That means if you consider this grid, then we find that this particular grid cell, it has multiple lines passing through it. Okay? So when the multiple lines are passing from it, this basically says that this particular M and B is the M and B, for which if we get a line, that line will actually pass from multiple points. Okay, because here you have intersection of multiple lines in this grid. Okay, Let us just consider, let's say, this particular grid in a grid cell. So in this particular grid cell, you see that there's only one line which is passing from this. So you can say that this particular grid gets just 1 volt. 1 volt means if you consider this B and M, you will get a line which will actually pass from only one point in the image space or feature space. If there is a point where, let's say, two lines are intersecting, so corresponding to that B and M, we can say that the line whatever we get, that will actually pass from the 2 points. Similarly, if we say that there is a point where in this space where there are multiple lines which are intersecting to each other, so we can say that we can very clearly say that corresponding to that B and M, we have a line which passes through many points in the image space, right? And we are actually looking for such lines. So when we are using the Hough transform to fit a model and line in this particular case, first thing is that we have, for each edge point, we have to vote for the possible parameters in the Hough space that we have already done. From when we are moving from here to here, and we get this kind of line plotting in the second image here, we have this process is basically voting with respect to each feature point in the parameter space. Okay. Once this is done, then what we have to do, this process of voting will actually accumulate the votes in the discrete bins that we have defined here. And once this accumulation is done, we have to find out a grid cell in this whole space where you have lot of votes, right? And wherever you have lot of votes, that will actually define a model corresponding to which, if you go to the feature space or to the image space, you will see that model actually passes through multiple points there. Okay. So this is the whole procedure of detecting the lines in any given image. So normally in this whole process, our input will be an edge map where we have already performed the edge detection, and we have got edge pixels like this. And then for corresponding to each edge pixel, as I just mentioned these steps here, corresponding to each pixel, considering that it is x0, y0, let's say we have to find out a line in the Hough space. We have to plot that line in the Hough space, and then we have to consider another feature point from the image space. Corresponding to that, we have to again plot a line here in the Hough space, and then once all the edge points are processed, then we have to go to this grid in the Hough space, and we have to find out the grid cells are the M and B values for which the more number of votes have been actually casted, and corresponding to that we can declare the suitable model. Okay. Now when we are using this the parameter space based on M and B, there's one thing you can notice from here. Whenever you have to plot all these lines, we need to know what is the maximum M that we have here. What is the value of M that we are going to consider in this axis, right? Similarly, we have to also need to know what is the value of possible value of B that we are going to consider here, because if these limits are not known, then when you are going to plot a line which runs from -infinity to +infinity, how will you draw it? Okay. What basically I mean here is that, suppose you have M space here like this, and M defined in this axis and B defined in the vertical axis. Now you have to plot a line, let's say this. So how far you will go and plot this line? So unless you know that this M is only up till this point, if let's say you say that this M is only up till this point, then this line will be only plotted up till this point, and then whatever B and M are falling on this line, they will define the corresponding M and B parameters to the points corresponding to which you have plotted this line here in the Hough space, right? So to plot any line in the Hough space, we need to know what is the maximum M and what is the maximum B we have. Now, if we analyze the possibilities of M and B when we are defining our line as y = mx + b, mx plus c, we see that this m can be also take infinite values, and this c can also take infinite values. In fact, they can, I mean, like c, it can take minus infinity to plus infinity, or even m can take the values from minus infinity to plus infinity. So if we consider our representation of line in terms of y equal to mx plus c, the m and c, they are going to take infinite values. Okay. And you know that when we are going to process this in computer, we don't have infinite memory, so we want limited. I mean, we have limited memory. So if we have such representation where we have to represent infinite values, we can't do that. Okay. So this is one problem when we are using this representation of line in terms of y equal to mx plus c. And similarly, there's another problem also associated with this model when we are using for line. It actually cannot define the vertical lines, because for the vertical lines, I mean, you know that m is nothing but tan theta, and tan 90 will be infinite. So you can't define the vertical lines also here, right? So to handle these situations, actually we go for another representation of the line, which is in polar system, okay, in the polar coordinate. And we know that in the polar coordinate system, a line is defined like this: x cos theta minus y sin theta equal to d, where for the line, d is the distance from 0, 0, perpendicular distance of the line from the 0, 0, and theta is the angle made by the this perpendicular from the x-axis. Okay. Using this representation also, we can define the line. Now the advantage in this representation is that we have the limit now on both the parameters that are present here. What are the parameters that we have in this equation? Two parameters, theta and d. As we had when we are defining y equal to mx plus c, we have two parameters m and c. Similarly, when we are defining the line in polar system, we have two parameters, theta and d. Now these theta and d both have the limits. Theta, very obviously, we can see that theta cannot go beyond 360. So you can say that theta varies from 0 to 360. So this theta axis can be defined by this, by using the values between 0 and 360. Similarly, we may think that d can be infinite, but if any image is given, in that image, this d can only take the finite values. Right? So, for example, if you have an image like this, where you have done you have done the edge detection and you have some edge pixels, in this image, you cannot have lines beyond this boundary that you have here. Right? So you cannot have any line here. All the lines that you are going to get in this image, they are going to be, I mean, only in this particular region. Right? So based on the coordinates of the image, or based on the size of the image, we can actually find out what can be the maximum d that you can have when you are representing the line in the polar coordinate. So when we are going for this representation, theta and d both can be actually can be defined. Their range, their maximum values can be defined. So that is why in place of doing the Hough transform in this model space, we normally do this in the polar coordinate system. Okay. And the procedure is very much similar. In case of when we are representing our images, sorry, our lines using y equal to mx plus c. So here the voting was done for parameter m and c. Now in this case, and we were considering possible x and y, and then we were voting for m and c. So in this case, again, we are going to consider possible x and y, and for all those possible x and y, we are going to vote for theta and d. Okay, so the procedure is very much similar. So our line is going to be represented like this. Now we can assume that there is a grid, as we saw in the case of y equal to mx plus c. Here, this grid was defined in terms of m and b. Now here we can say that this is there's a finite grid which is defined in terms of theta and d. And if you, let's say, in computer, when you are making a program, you can assume that this is a kind of 2D array, and initially all the values of every cell here corresponding to a d theta, it has initial values 0. Now when we are considering different x and y, and then when they are voting for these parameters, then we'll see that more and more votes will accumulate for these cells. but at the initially you can assume that this is 0, 0. Okay. So for each edge point, we have to consider the corresponding xy, and for corresponding xy, here we have to consider all the possible values of theta. Let us say it is ranging from 0 to 180. You can see that when you are using 0 to 180, we can represent all the possible lines. So for a given xy, for all possible values of theta, we can actually find out the possible d, and based on that, we can update this matrix H, matrix H. If you, let's say that this matrix is H, for every for every value of x and y, all the model parameters for which if you define a line, that line passes from xy, they will get 1 volt, right? So for a particular xy and for all possible values of theta, that s d theta combination will be incremented by 1, because they all will get 1 volt. Okay? And once that is done, then you have to find out in this grid, you have to find out the place where s d theta has more votes. If you know that there is only one line existing in the image, then you can actually look for the maximum, d theta, or the cell here which has the maximum votes, and based on that you can declare the presence of line and or find out the parameters for the line. If you have multiple lines, then you can look for the places where you have more votes, and based on that you can decide the possibility of lines. Okay, so that way we are detecting the so this from the step 3 you will get a d theta where you have more votes, and corresponding to that d theta you can define the line. Okay, and that line can be actually fitted on the edge image. When we are talking about the complexity here, if you just analyze this complexity is nothing but actually the number of computation that has been done for voting. So if you just count how many votes you have casted here, that will actually directly tell you the complexity of this process. These are a few examples. So let's say this was the input image. There was only one line. So in the half space, you see that there is only one bright point. I mean, if you represent this grid structure in terms of in terms of image, then you find that corresponding to this, there will be one place where data votes are there, corresponding to that you have white pixel here, right? If you have any image in the half space like this basically tells that there are 4 lines. Okay, there are 4 lines because there are 4 bright spots. Similarly, in this image, you have some set of lines like here, 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 here. These lines corresponding to that, you see that this line, corresponding to that, you see that there are some bright spots here. Okay, these are a few real examples. So this was the input image. After edge detection, we got this one, and then when we perform the Hough transform, we got this image. And corresponding to these Hough parameters, if you just find out the corresponding lines and if you plot them on the image, you will see a structure like this. Right? Wherever you had line in the building, you see that those green lines are plotted here. Okay, similarly, this is another example. Okay, so there's another example here. You see that these points are not falling on exactly on the line, so that is why you don't get a very sharp place. You don't get any very sharp spot here. You have a kind of little distribution. So to handle such scenarios, actually, when we are putting the grid, we have to suitably choose what should be the size of the cell, so that we can actually manage this kind of scenarios. Okay. This is a noisy case. You see this in this particular example, there is no line existing, so that is why you don't get any very clear-cut spot in this image, which can tell you that there is a line in the image. Okay. In the previous algorithm, we saw that we have considered all the possibilities of theta. But if you remember, when we were discussing the edge detection, we said that whenever there is a line, there is an edge in the image, the direction of edge is actually perpendicular to the direction of the gradient. So if you know the direction of the gradient, actually you know the direction of the edge. And now here we are saying that those edge points are going to fit in the line. So we can say that the direction of line is actually going to be perpendicular to the direction of the gradient. So actually, by using the value of the gradient, we can actually find out what should be the suitable theta for which we should do the computation. We don't need to do computation for all possible theta from 0 to 180 degrees. We just need to do the theta uh, which we actually get from the gradient. For that particular theta only we need to do this computation, and that theta can be actually directly used, because if you see this representation here, we are looking for this theta is nothing but actually the direction of the gradient. Okay? And when we are representing this, we are actually looking for this direction. So this from the edge image, if you can just get the direction of the gradient, that can be directly used in this equation, and then in that case we don't need to go for each possible computation for theta equal to 0 to 180 degree. We can just directly get the gradient value, and for that only we can compute the d, and based on that we can update the matrix H. Right? So this algorithm is exactly same as the previous algorithm, but only we are not iterating for theta. We have just fixed theta here. Okay, and by using this fixed theta, we can compute the existence of the line. Okay, so the possible extension, whatever algorithm we have discussed for the for the line when it is represented in terms of polar coordinates, this was the extension one that we just talked about. Second extension actually can be by considering the magnitude of the gradient that you have for the H pixels. So we can assume that wherever the magnitude is high in the edge image, that corresponding pixel is more reliable pixel. So we can say we can actually consider the magnitude of the gradient to actually find out the strong H pixels, and wherever the strong H pixels are there, we can actually give more votes to those pixels. Maybe we can say that the voting actually casted by a particular H pixel is proportional to its magnitude. If its magnitude is more, its vote will have more weight. If it is the magnitude of the gradient is less, its weightage for the vote will be less. Right? In the previous examples, in all these algorithms, we have given equal importance to all edge points. Every edge point was able to cast one vote corresponding to the model parameter. But here we are saying that we can have an extension where we can give more weightage to the stronger edge pixels. Another extension we can have here by having different resolutions that we are going to have for the grid that we are defining, like we have defined here the grid for the d theta. So for different values of the resolution that we are going to have here, we can have different outputs. Okay, and with this we'll stop. The fourth extension to this is actually I mean, we'll see it in the direction of circles and squares.